Welcome to problem set 19. Our problems today will be from the topic monosaccharides. Before we get started, just a quick reminder that the worksheet to accompany this video is available online through my website. And with that said, let's get started with number 1. Label the following as dextrorotatory or levorotatory. So I already wrote A through D up here on the board. Remember that the capital D and the capital L do not stand for dextrorotatory and levorotatory. They simply tell you the orientation of the lowest chiral carbon hydroxyl in a Fisher projection. If that hydroxyl points to the right, it is dextro. We label that with a capital D. If that hydroxyl points to the left, it is in the levo position. We label that with a capital L, but that does not mean that it rotates plane polarized light to the right or the left. It doesn't tell you which way it rotates plane polarized light. The only way that you can know this from the name is if we include the plus or the minus in the name, and it's not always included. I did include it here, otherwise you'd have to go look up in a reference book. So we can see that D-glucose, because we have the plus here, it must be dextrorotatory. It rotates plane polarized light to the right. So I'm going to write here dextrorotatory for D-glucose. D-mannose also has a plus, so it is also dextrorotatory. D-fructose has a negative, so even though it is the D isomer, the D enantiomer, we can see that it is levorotatory. That is, it rotates plane polarized light to the left. And L-fructose, of course, then has to be the dextrorotatory enantiomer. Okay, so going on to number 2, match the pairs below with the word that best describes their relationship. Enantiomers, diastereomers, anomers, or structural isomers. Hint, relationships can be used more than once. Okay, so for A, we have D-glucose and L-glucose. The D and the L are designating an enantiomeric pair, non-superposable mirror images. In D-glucose, the hydroxyl group off of the lowest chiral carbon is pointing to the right. In L-glucose, it's pointing mirror image to the left. So A are enantiomers. B, alpha D-glucopyranose and beta D-glucopyranose. Alpha and beta forms of a cyclic hemiacetal, a monosaccharide in a cyclic hemiacetal form, are known as a special type of diastereomers called anomers. Make sure you know that term. So B, those two molecules are related as anomers. C, D-glucose and D-galactose. You may not know these structures, and your instructor may or may not want you to memorize how to draw these structures. So go ahead and take a moment to look back in the tutorial notes if you have them handy. I have already drawn them on slide 2, so you can look those up. I'm going to go ahead and draw them on the board as well. So glucose, D-glucose, D because this is to the right, okay? And let me label that D-glucose. And then what is the other one? D-galactose. Okay, so let's draw that over here. You might remember from the tutorial that they definitely have the same molecular formula, C6H12O6. So they're definitely related as some type of isomers. We already know that. And again, if you don't know those structures, you can just look them up on slide 2 as needed. And this is D-galactose. Okay, so the relationship between these. Clearly, these are not enantiomers. The enantiomer of D-glucose is L-glucose. However, they do have the same molecular formula. So they're some type of isomer. They do have the same connectivity of atoms. Notice an aldehyde, followed by a chiral carbon with an OH and an H, followed by another chiral carbon with an OH and an H, followed by a third chiral carbon with an OH and an H, followed by a fourth chiral carbon with an OH and an H, and last but not least, a CH2OH. So they are a type of stereoisomers. Same molecular formula, same connectivity of atoms. How they differ is in the three-dimensional arrangement of those atoms. Now they are not enantiomers, so they must be related as stereoisomers that are not enantiomers, diastereomers. So I'm going to write for C, diastereomers. And one more to go. D, squeak it in down here. Okay. We have L-glucose and L-fructose. Okay. Now you might remember, and if you don't, you can look back to slide 2 of the tutorial notes, that glucose and fructose do have the same molecular formula. They are both hexoses, so C6H12O6, but glucose is an aldose, meaning it has an aldehyde at position 1. Fructose, remember, is a ketose, meaning it has a ketone at position 2. So clearly, they are isomers that do not have the same connectivity of atoms. Okay? That means that they have to be related as structural isomers. They have the same molecular formula, and that's it. The connectivity of the atoms is different. So let me write for D, structural isomers. Sometimes also called constitutional isomers. All right, so we are clearly out of room here. Let's erase before we go on to number 3. Okay, number 3. Label all functional groups in D-glucose drawn below and then complete A through C. So I've drawn it up here. So we're going to label all the functional groups, and I'll do that in a different color. I'll do that in blue. So we've got lots of alcohol functional groups. So I'll draw a line to all those. So alcohols, and over here as well. And then we also have an aldehyde. All right, now part A. Circle the 2 functional groups that will react during mutarotation to form a 6-membered ring. Let's do that in red. So we want the 2 functional groups that are going to form the pyranose form, the 6-membered ring form. So clearly the aldehyde, but the question is which alcohol functional group, which hydroxyl will it react with? So 1, 2, 3, 4, 5, 6. Remember that the oxygen will become part of the ring, so it counts as 6, and we want the one that will make the 6-membered ring. So it must be this hydroxyl group. I'll do that one more time. 1, 2, 3, 4, 5, 6. That's going to make the 6-membered ring. So that's part A. Part B, draw an arrow to represent the new bond that will form during the reaction described in part A. Okay, so let's go ahead and go to the green pen, and I'm going to go ahead and draw in my lone pair of electrons here. Okay, and I'll draw the arrow like so. Okay, so the ring's going to close like so. And part C, draw D-glucose in the alpha and beta pyranose forms. Okay. Let's go back to the black pen here. All right, so let's just go ahead and go through the whole sequence of steps to get to the closed ring, the cyclic hemiacetal, just like we did in the tutorial. So the first thing that we want to do is lay the Fisher projection down on its side to the right. Lay down to the right. Okay, so what we get here is our aldehyde functional group, and then our carbon 2, 3, 4, 5, and 6 is the CH2OH. Remember that everything that is on the right side is now pointing down. So all these hydroxyls are pointing down. The hydroxyl that's on the left is now pointing up because we just laid it down. Okay. So the hydroxyl at position 2 should point down. Position 3 should point up. Position 4 down, and position 5 down. Now we're trying to show the reaction with the hydroxyl at position 5. Right now it's not in position to react with the aldehyde, but single bonds rotate freely, and so we're just going to rotate this around to bring the hydroxyl into the closest proximity to the aldehyde here. Okay, so what that's going to look like, and this is not a chemical reaction, this is just rotating a single bond. Got the aldehyde, carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. And here's our OH. And now our CH2OH is pointing up, hydroxyl's down, up, and down, because none of those bonds changed. Just this last bond rotated. Okay. And let's go ahead and draw in our lone pair of electrons. And remember that this is not a mechanism, this is just a method that I use to help students understand where new bonds will form and where bonds will break. So we've got an attraction from the partial negative oxygen to the partial positive carbon of the carbonyl. Double bond turning into a single bond. Got the partial negative oxygen attracted to the partial positive hydrogen, and the breaking of the bond here. Okay. So remember, we're going to draw out the alpha and the beta form. So I'm going to put 2 arrows there because we know that the OH can point up or down from the anomeric carbon or the hemiacetal carbon there. So let's do the beta first. Which has the OH off of the hemiacetal carbon, the anomeric carbon, pointing up, down at the 2 position, up at the 3, down at the 4, and then the CH2OH is pointing up, same as the OH in the beta position. So this is our beta D glucopyranose. Now we need to do our alpha. Everything the same, except the position of the hydroxyl off of the anomeric carbon is now pointing down. Everything else is the same, so down, up, up. And this is the alpha D glucopyranose. Okay. And remember that in an aqueous solution, the alpha and beta forms are interconverting, and in order to do that, they have to go through this acyclic, this open chain form of glucose as well. All right, so that will conclude our problem set number 19. It was kind of a short one, but hopefully it helped to solidify some of those concepts from tutorial number 19. Thank you very much, and I hope you will tune in to tutorial 20.